So indicate. Oh, sorry, this drawing's a little bit wonky. So point P is there, the lowest point at the bottom of that hill. The lowest point is where the maximum speed of the car is attained. Then II, calculate the value at this point. So you say something like MEI equals MEF, MGH equals 1/2 mv squared, masses cancel. V is the square root of 2gh. So V is the square root of 2gh, and I'm sorry that looks so bad, but I don't know what to do about it. So this is 2 times around 10, which is 20, times 90, which gives you 1800. So this is around 30 times the square root of 2. So I think it's around, what, 52 meters per second? Is that what you got? 42. 42. Okay, bad math. Whatever. What's the square root of 1800?
Yes, 42.
Okay, sorry about that.
Oh, no.
Okay, questions? All right. Yes. So B says calculate the speed of the car at point B. So if this is point B, we want to know VB. Okay. So again, I go to MEI equals MEF because I just told you just use energy whenever you're looking at how things move around. What kind of energy does it have at A? PE. What kind of energy does it have at B? PE plus KE. Do you see that? Okay, hopefully you see that you could still fall and die if you went out of the car at point B. Right? 50 meters is like 160 feet in the air. And you would get jacked up in a serious fashion. So, here we have MGH at A equals MGH at B plus 1/2 MVB squared. Cancel the M's right away. And yeah, I don't know, like the easiest way to do this, I think, is just VB is equal to the square root of 2G times HA minus HB. Okay, and HA was 90, HB was 50, so that gives us 40, and then 2 times 10 is 20, so that's the square root of 800, which is 20 times square root of 2, so is that 28?
Oh, yeah.
Good, I got one right that time, that's good. I was beginning to doubt my own mental math capabilities. Questions on that? Pull that back down, and we move on to part C. Part C, I. On the figure of the car below, draw and label vectors represent the forces acting in the car when it's upside down at point B. So, okay, so we got the car upside down, right? See little people with their hands sticking out. Okay, we'll pick green and fatten this boy up. So we've got Fn and Fg. Any other forces that I may have missed? Oh, I'm sorry, I'm just rock and rolling through this because I want to get as much done as possible. Then it says calculate the magnitude of all forces identified in CI. So then we're supposed to go back and we say the sum of the forces, whatever, at point B is going to be equal to MA. And in fact, What kind of acceleration is it experiencing? Centripetal acceleration. So that becomes mv squared over r. Okay, and remember, A points towards the center, so these two are both positive. So we get Fn plus Fg equals mv squared over r. And so then we can say Fg is easy, right? We know that. And mv squared over r is easy, because we know that. Do you see this? Oh, sure. Well, mg, we know Fg, right? That's just the mass of the cart times gravity. And then we know, let's say, F sub c, because that's mv squared over r. And v is from part B, right? It's from part B. And we know the radius is 20 meters. Everybody with me on that? Okay. So the only one we need to calculate is Fn. So I say Fn is equal to mv squared over r minus mg. We get 700 times v squared over r minus gravity. So v squared, 28 squared, I have no idea what that is, but it's got to be around like 800 something. 784? Okay, there you go. 784 divided by 20, so that's easy. That's like 390 or something. And then minus, or I'm sorry, 39. Minus 10 is like 29, so 29 times that gives you 20,000, something like that.
Oh, cool.
So it's like around the area of 20,000 newtons. What does it come out to? 20,000 what?
20,580.
20,580? Yeah. Okay, so 20,580 with a ridiculous number of significant figures. That's only 4. Okay, then part D. Part D says, suppose the friction is not negligible, how could the loop be modified to maintain the same speed at the top of the loop as found in B? So if we want to have the same speed at the top of the loop, but we now have to overcome friction, what do we do? Number one, if you say raise point A, now actually take a look at the question. Suppose that friction is not negligible, how could the loop be modified? Uh-oh. See what happened there? So is this answer overall legitimate? Yeah, in terms of its absolute, it is legitimate. But pay attention to the question. It says you have to move the loop. Okay? So, we can't raise A, but what could we do that's the same thing? Okay, we could lower B. Do you see that B is 10 meters off the ground? Oh, not a B. Do you see that the loop that B is on is 10 meters above the ground? Because B is at a point of 50 meters, but the diameter of that loop is 40. So you could drop that loop down onto the ground. Does that make sense? Okay, I mean, I guess you could dig a hole and make it go down if you want. Okay, and then the other thing I saw some people's, let's see, give you a chance to, Carol, do you have anything else besides that? Okay, anyone else have anything else besides that, besides table 1? Yeah. Okay, and table 1 was saying that too. Make the loop smaller. Wow, that is like completely illegible.